Hi, in this second concept in quadratic equations, we'll be looking at a very fundamental but yet very important concept called which relates to the sum and product of the roots of a quadratic equation. So suppose we have a quadratic equation ax square plus bx plus c equal to 0 and alpha beta happens to be its roots. So it turns out that the sum of the roots alpha plus beta will always be equal to minus b by a, and the product of the roots will always be equal to c by a. Right? So the sum of the roots and the product of the roots, if these are the two values that you need to find out, their value only depends on the coefficients. Right? You don't actually have to find the individual values. So the sum of the roots again is coefficient of x by coefficient of x square minus sign, and product of the roots is constant term by coefficient of x square. So as an example, again, if you have a complicated quadratic equation, something of this form, maybe if you have this quadratic equation, so now obviously the roots will turn out to be fairly complicated. But as long as the question is about finding the sum of the roots or the product of the roots, you actually don't have to find the roots. So the sum of the roots will directly be minus 2015 by 2014, and the product of the roots can directly be said to be 2016 upon 2014. Proof for something like this would be very straightforward. So again, suppose alpha is minus b by 2a. We've already found the roots of the quadratic. Suppose alpha is this particular root and beta is this particular root. Right? So what I can now say is that alpha plus beta, just substitute. And similarly alpha into beta will be. Right? So let's apply this idea to some problems now. Right? In the first problem, we've been given a quadratic equation. There's an unknown a over here, and it's been given that the roots are squares of each other. So one root is alpha and the other root is alpha square, and you want to find the value of a. So again, let's go to our relations. The sum of the roots should be 6 by 8, so that is 3 by 4. And product of the roots, that must be a upon 8. Right? So these are two equations that we get, and now we want to eliminate alpha from this. So let's cube the first. So that will give us alpha cube plus alpha raised to 6. And substitute the value of alpha cube as a by 8. So a by 8 plus that gives you a base that, so you've eliminated alpha, you get a quadratic in alpha, and then you just need to eliminate alpha. You've eliminated a, and you got a quadratic in. You eliminated alpha and you got a quadratic in it. So just solve for it. So 8a plus a square to 18, 27. A square plus 26a minus 27 equals 0. So simple quadratic, you can factorize it, get the value of a as minus 27 or 1. Right, so again we used the sum of the roots and product of the roots relation, eliminated, we got two equations involving alpha, eliminated alpha from both the equations, got the quadratic in a, solve for a. In our second question, we've been given an equation and we've been told that the roots happen to be equal in magnitude, numerically equal. That means the magnitude is the same, but they're opposite in sign. So that effectively means that the roots are negatives of each other. So we want to use the fact that the roots are negatives of each other. So let's first simplify the equation to the general form. Rearrange terms. We should get something like so if you get all the terms to simplify and get all the terms to one side, you get this particular equation. Now again, what we know is that the roots are negatives of each other. But if the roots are negatives of each other, the sum of the roots must be 0, which gives us that A plus B. So in this problem we've been given two quadratic equations, and what's been given to us is that the roots of both the equations happen, the ratio of the roots of both the equations happen to be the same. So again, suppose this has roots alpha 1, beta 1. And this has roots alpha 2, beta 2. So what do we know? Alpha 1 upon beta 1 should be the same as alpha 2 upon beta 2, which means that alpha 1 by alpha 2 is the same as beta 1 by beta 2. Right? So now by properties of ratios, since these two ratios are equal, these two ratios should also be the same. And that's it. So again, so alpha 1 plus beta 1 is minus P, alpha 2 plus beta 2 is minus A, alpha 1 into beta 1 is Q upon P. Square and cross multiply, so P square B must be the same as A square Q. So in this particular question, we've been given a quadratic equation, and it's known that the roots of that quadratic happen to be equal, and we want to prove a certain relation between A, B, and C. So a certain observation will help a lot in this particular question, and the observation is that if I put x equal to 1, then the left hand side goes to 0. So again, an observation is that right? So again, if you see, if I put x equal to 1 and I look at the left hand side and I open up all the brackets, AB minus AC plus AC, BC minus BC, everything gets cancelled out and the left hand side becomes 0. Now the fact that the left hand side is becoming 0 automatically means that the sum of that x equal to 1 happens to be a root of the equation. But since x equal to 1 is a root of the equation, so 1 is definitely a root of the equation, and you've been given that the roots are equal. So that would have to mean that both roots are 1. That would have to mean that product of the roots is also 1. But product of the roots happens to be, we'll have the constant term by coefficient of x1. So just rearrange terms over here. This is a past ID problem, and it might look a little complicated, but again, if we just kind of stick to basic ideas and proceed in a systematic manner, we'll be able to tackle the problem. And again, we'll essentially be only using the sum and product of the roots idea. So again, there's a product of 4, there's a multiplication of 4 brackets on the left hand side. So let's multiply the first two first. So if I alpha minus gamma into beta minus gamma, so that should be alpha beta minus gamma into alpha plus beta plus gamma square. Right? But alpha and beta are the roots of this equation. So alpha into beta is 1 plus gamma square minus alpha plus beta itself is minus of P, so I get plus gamma times P. Right? So the product of the first two brackets gives me this expression. Then suppose I do a similar thing with the third and fourth bracket. So alpha plus delta into beta plus delta. So again, this should be alpha beta plus delta square plus delta into alpha plus beta. Again, the same thing. Alpha into beta is 1, alpha plus beta is minus P, so 1 plus delta square minus delta times P. So we made some progress in the sense that at least now the left hand side only involves, instead of, initially we kind of got rid of alpha and beta at least, but we're still stuck with gamma and delta, right? And we got P over here. So just take a moment and think about how can Q come into the picture. So again, the final, if you want to get this as the right hand side, you'll somehow also have to get rid of, we'll be multiplying these two brackets, and in doing that we want to get rid of gamma, and at the same time also introduce Q. So just take a moment and think about how that can be done. That just requires one observation, the fact that gamma and delta are roots of this equation, right? So since they are the roots of this equation, they'll satisfy the equation. So, this equation can be rewritten as x square plus 1 equal to minus qx. And again, what's been given is that gamma delta are the roots of this equation. So what must happen is that gamma square plus 1 must equal to minus q gamma, and delta square plus 1 must equal to minus q delta. Right, so now I think we're almost done. So our left hand side was again the product of these two brackets. Now gamma square plus 1 is minus q gamma. So minus q gamma plus gamma p into delta square plus 1 again is minus q delta. So that finally gives us q square minus p square into gamma delta. But since gamma and delta are the roots of this equation, gamma into delta itself clearly is plus 1. So the left hand side finally reduces to q square minus p square, which is something that we have to prove. Again, this is a past IT problem. Alpha, we have a quadratic equation whose roots are given to be alpha and beta. And there's another quadratic equation involving a, b, and c. And what we've been asked to do is we want to express the roots of the second equation in terms of alpha and beta, right? So one thought in this question could be that let's basically try to get rid of a, b, c completely, so that we are only dealing in alpha and beta. That might make it easier to identify the roots of this equation in terms of alpha and beta, right? So just think about how could that be done. So from this equation, how can I completely get rid of a, b, and c? What I again know is that alpha plus beta is minus b by a, and alpha into beta is c by a. Right, so if you want to basically get rid of a, b, c, you will need the ratio b by a and c by a. So what we would do is I could divide by a cube throughout. Right. So if we do that, what do we get? X square plus b by a into c by a, x plus and now let's put the value of these ratios. So b by a is minus of alpha plus beta, c by a is alpha into beta, x plus alpha cube beta cube. Let's rearrange terms a bit. This is x square minus alpha square beta plus beta square alpha. This can be thought of as alpha square beta into beta square alpha. This clearly can be factorized in this particular way. When I expand these two brackets, I'll clearly get this value, right? So the roots are alpha square beta or and that's our answer. So the roots of the second equation in terms of alpha beta are simply alpha square beta and beta square alpha. Related to the sum and product of roots is something known as the symmetric function of the roots alpha and beta. Okay. So first of all, let's just try to understand what do you mean by symmetric function of alpha and beta. So again, a function of alpha and beta would refer to an expression involving alpha and beta, and a symmetric expression in alpha and beta, a function of alpha and beta, will refer to an expression which essentially is symmetric with respect to alpha and beta, which effectively is saying that if you were to interchange beta and alpha, then the overall expression should remain exactly the same, right? So we'll define, again informally, we can define a symmetric function of alpha and beta as some expression involving alpha and beta which remains unchanged on interchanging alpha and beta, right? So function, expression in alpha and beta which remains unchanged on interchanging. So if you think about the simplest symmetric expressions in alpha beta, they clearly are the sum of alpha plus beta and alpha into beta. These clearly are symmetric expressions, and these also happen to be, these are, in fact, for two quantities, these will be referred to as what are known as symmetric, the elementary symmetric expressions of alpha and beta. In the sense that these are the two simplest symmetric expressions in alpha and beta. Alpha plus beta and beta alpha into beta. If I interchange alpha and beta, obviously I'll get beta plus alpha and beta into alpha, but the overall value remains the same. Other examples now will be, again, something like alpha square plus beta square, alpha cube plus beta cube. In fact, in general, alpha raised to n plus beta raised to n. Alpha square beta plus beta square alpha. Alpha pi beta plus beta pi. So all these are examples of symmetric functions. Something like alpha minus beta is not a symmetric expression, clearly. Because in alpha minus beta, obviously, if I were to interchange alpha and beta, the expression will be negative of the original one. So you get beta minus alpha, which is the negative of alpha minus beta. But if I square this, so something like alpha minus beta whole square, or something like mod of alpha minus beta, these two obviously become symmetric expressions in alpha and beta. If you want to define a symmetric expression slightly more mathematically, I can say that if f of alpha comma beta, if this refers to a function of two variables alpha and beta, then f of alpha beta is a symmetric expression if f of alpha beta is the same as f of beta comma alpha. Which is basically again saying the same thing, that if you were to interchange alpha and beta, the value of the expression remains the same. So now a very important idea is that for two quantities, again alpha and beta, the value of every symmetric expression in alpha and beta is finally can be reduced or finally can be expressed in terms of alpha plus beta and alpha into beta, which were the two elementary symmetric expressions. You can kind of extend the idea to three more quantities also. So for three quantities alpha, beta, gamma, the elementary symmetric expressions would be alpha plus gamma, alpha beta plus beta gamma plus gamma alpha, and alpha into beta into gamma. So again, for three quantities, you'll say that every symmetric expression in alpha, beta, gamma can be expressed completely in terms of the three elementary expressions, right? But for the time being, again, we are only concerned with two. So every symmetric expression in alpha and beta can be expressed in terms of alpha plus beta and alpha into beta. Okay. So some basic identities, alpha square plus beta square will obviously be alpha plus beta whole square minus 2 alpha beta. Alpha cube plus beta cube will again be alpha plus beta whole cube minus 3 alpha beta into alpha plus beta. Alpha minus beta whole square will be alpha plus beta whole square minus 4 alpha beta, etc. Similarly, something like this will be alpha beta into alpha plus beta. This will be alpha square plus beta square upon alpha beta, and so on and so forth. So the kind of problems then therefore can be created that if you're given a quadratic equation and you're given its roots as alpha and beta, since we know the values of alpha plus beta and alpha into beta, we can therefore evaluate the value of any symmetric expression in alpha and beta also. This last identity is kind of important because it is essentially getting related to the difference of the roots, right? So we can come up with this important result. So if this is my quadratic equation, then the square of the difference of the roots will turn out to be the discriminant value upon a square. That's pretty obvious. So you'll have b square by a square and 4c by a. So you'll have b square minus 4ac by a square, right? So whenever you want to talk about the difference magnitude, again in terms of magnitude, I can say that the magnitude of the difference between the roots will be the square root of the discriminant upon the magnitude of a. So again, this result is very useful when the difference of the roots is involved in the problem. So as a simple example, this is a problem that we have an equation x square plus bx plus q equal to 0 and its roots happen to be two consecutive odd integers. So then I can simply say that alpha minus beta square will again be b square minus 4q discriminant upon a square. But since alpha and beta are two consecutive integers, the difference, magnitude of the difference is 2 and its square becomes 4. Suppose we are again a pretty straightforward problem. You just alpha beta the roots of a given equation, and you want to find out the value for all these symmetric expressions. So again, the roots will not be very straightforward. You'll get irrational roots over here. But then again, the point is that to find the value of a symmetric expression, you don't actually need the individual values. You just need the sum and the product. So again, the sum of the roots is known to be minus 2. The product is minus 4. Let's put the values alpha plus beta cube. That'll be minus 8. Minus 3 into minus 4 into minus 2 or minus 4. So this will be minus 12, 24. 24 and 32. Minus 32 by minus 4 plus 8. C part again we have a standard result. Square of the difference should be the discriminant, which is b square minus 4ac. So that's 4 minus 4. That's 20. Now in the d part, we've already found two values. So alpha square plus beta square had turned out to be how much? Alpha square plus beta square had turned out to be 4 minus 2 into minus 4, so 12. And alpha cube plus beta cube had turned out to be how much? Minus 32. If I multiply these two values, I'll get something like this. Okay, so just let's substitute values. So 12 into minus 32. Alpha square beta square. Alpha into beta again is minus 4, so square should be 16. Alpha plus beta is minus 2. That will be how much? Minus 32 plus 32. So 32 into 11. Now in the E part, although it is a symmetric expression, but if you start simplifying it directly, it will kind of become fairly complicated, as you can very well imagine. So actually I intended the question to be something else. So let's change this to so this is the question, right? So where an observation again is that this expression can actually be simplified further. So alpha is the root of this particular equation, so it should satisfy it. So if I multiply it by alpha on both sides, I get alpha cube plus 2 alpha square is equal to 4 alpha. So alpha cube plus 2 alpha square minus 3 alpha should simply be alpha. So this value in the bracket is simply alpha, and this value similarly in the bracket will turn out to be beta. So the E part, the value that you want to find out is which then becomes again very straightforward. Again, alpha plus beta square had turned out to be 12, and alpha into beta whole square will be 16. So that will be 3 by. I have this past IIT problem. Right? So for the first equation, the roots are given to be alpha comma beta, and for the second equation, the roots are given to be alpha plus delta comma beta plus delta. Okay. So let's call this alpha 1. One of the ways of this, something has to be proved. Now, one observation in both the cases is that for both the equation, what remains the same is the difference of the roots. The roots over here have basically been obtained by adding, adding a constant to both alpha and beta, the same constant to both alpha and beta. So which obviously means that the alpha 1 minus beta 1, the difference of roots over here and over here happen to be the same. So alpha 1 minus beta 1 square is definitely the same as alpha minus beta square. And that's it. So the difference, square of the difference of the roots over here should be the discriminant value by capital A square, and over here it should be. That completes our second concept, which again dealt with sum and product of the roots and the idea of symmetric function of roots. Thanks.